So what's a truth table, Nick? Didn't you write a program that outputted truth tables? And then didn't we do it in class last time? But I assume you watched the video. So,
I snapped it on Xbox while I was playing this.
are you even lying about that?
No, I seriously did.
It's well, I know of the feature. So what is a truth table? You wrote a program to create them, right?
Yeah.
But you know what they are.
Isn't it just a table that shows outputs of truth, a truth or a false?
Yeah. Well, the starting point would be it's a table. Did you give me? You didn't give me even a table. The least you could have done is literally drawn me a picture of like a dining room table. That would have been worth more points.
Really?
Probably. All right. So, how many unique variables do we have in this particular Boolean expression? 2. So, how many possible inputs do we have? 0, 0, 0, 1, 1, 0, 1, 1. Right? Those are our possible inputs. So, we have 0, 0. 0, 1. 1, 0. And 1, 1. Okay, so those are our inputs for this guy. And then we should have one column for our output. So if A, and here I'll even just label these. This is our A. This is our B for our inputs. So if A is 0 and B is 0, this whole thing here is knotted. So 0 and 0, this is the AND symbol, right? So 0 and 0 is what? It's false, not that. It's true. True or, doesn't matter what this guy is. This whole thing is true, right? Because we have at least one true on a side of an or. So now we have true and B is false. That's a 0. So true and false is what? True and false is false. So you could have put a false or you could have put a 0. Either one's fine. All right, 0, 1. 0 and 1 is false. Flip it to true. Doesn't matter what this guy is. B is true. True and true is true. 1 or 0. The B is false. Doesn't even matter what the heck happens over here. See how easy this actually ended up being? We don't even need to do the crap in here. Anytime that B is a 0, this whole thing is going to be a 0. Because of this B right here. It's part of an AND. Last one, 1 and 1 is true. Flip it to false. False or 1 is 1. So this is a true on this side and true in the B. So this is a 1. That make sense? How many of you got that right? This was my row.
It's not the same symbols as in discrete, so I got confused.
Yeah, you're in this class.
Yeah. Well, I didn't know.
What?
It's not the same symbols he uses.
But do you do truth tables in discrete?
Yeah.
Do they look like this?
No.
Well,
What do your truth tables look like?
Yeah, but we do
truth
all this
table
stuff.
does not
Hmm.
change the symbols. That's about it, though. Use T's and F's, and then use logic symbols. Or
Right. So this is T. This is FF,
Yeah,
FT.
it's the same thing.
No, I mean like in the equation.
Oh, yeah.
Well,
Like
you have to learn those.
No, but we've covered this in here.
the overhead line, I know, is not the same in discrete, but that is the same in logic.
So what's the problem?
The classes just meld together. I get a little confused.
Okay. So this makes sense? And we actually have a program that can produce this for us, right? We can actually write this expression using our gates. Okay. So what we're going to do is we're actually going to jump ahead 2 chapters. The things we're skipping. Something called sums of products and Karnaugh maps. These are representations of Boolean expressions. Important-ish, but not worth the time given that we have 2 classes left. Okay, so just understand that that's kind of what we're jumping over, is different ways of representing digital circuits. So then we're going to talk about next is adders. Okay. So a bit bigger here. Let's just go down more. Okay. So, an adder. When you think of the word adder, what do you think of besides a snake? Do you know there are snakes called adders?
I don't know that many people thought of a snake when they heard that.
Really?
I don't think so. I thought of addition.
Okay, yeah, addition would be the good thing to think about, right? So specifically in digital logic, an adder is the addition of exactly 2 bits. All right, and as we're going through this, I want you to think about this in terms of how computers are actually built and how this stuff starts relating to size of integer and size of long, things like that inside of our computer, where we can't necessarily just add arbitrary size pieces of information because we're working with a limited set of hardware. Yes, it's very, very tiny inside of our computers with very, very large scale integration, but if we built physical adders in the, I don't know, made these out of vacuum tubes and stuff, go back to the old days, even adding relatively small numbers together could take up this whole classroom in machinery. So, an adder. Most mathematical operations can be handled with addition. We've seen that a whole bunch of times. So we've seen binary addition. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is a 0 with a carry bit. Okay? 0 with a carry bit. So that carry bit comes into play here, that we have to represent that somehow in hardware. So these are our 4 possible results for adding 2 bits. Okay, so here's a diagram of something called a half adder. 2 inputs. Each input is a bit. 2 outputs. We have the sum and we have the carry. Inside here, it's doing the magic that produces these outputs. If I feed it a 0 and a 0, it's going to produce a 0 and a 0. 0 for the carry. 0 and 1, it'll produce a 1 and a 0. 1 and 0, it'll produce a 1 and a 0. 1 and 1, it'll produce a 0 and a 1 for the carry. Okay? So these are the possible inputs that we just discussed. How is an adder actually implemented? So before I scroll down, if we have a truth table, we have a truth table for our adder. We have the sum. And we have the carry. So 0 plus 0 is a sum of 0, carry of 0. 0 plus 1 is a sum of 1, a carry of 0. 1 plus 0 is a sum of 1, a carry of 0. 1 plus 1 is a sum of 0, a carry of a 1. Okay, so this is our truth table. 2 inputs, 2 outputs. If I just gave you a bunch of parts, how could you build an adder? What if you were asked to implement an adder? Go ahead.
Sum would be an OR, the carry would be an
Okay, sum would be an OR of these guys. So we have a 0 or a 0 is a 0, a 0 or a 1 is a 1 or a 0 is a 1 or a 1 is a,
exclusive OR.
okay, exclusive OR, right? All right, so you want sum is an XOR, and what's the carry? Carry is an AND. Okay, you see those two patterns there? How do you build an XOR? I'm going to break this down even a little bit more. Let's say I want to build an adder using only ANDs, ORs, and inverters. That's what I'll give you. Not and. For what?
Exclusive OR.
Is it exclusive or not and? If this is our exclusive or, wouldn't this be a 1 as well? For not and? So not and's correct here. It's correct here. It's correct here, but it's not correct here. So how would you build an XOR? We wrote code to do this as well. Start off by brute forcing it. An XOR means exactly one number is a 1. Correct? Okay, well, how do we do one number is a 1? If I have an A and B, how do I return true if only one of them is a 1? Go ahead.
A or B and not A and B.
A or B, in parentheses, right?
Yeah.
And A or B, not that. Is that what you said?
Not A and
Oh, A and B. So A or B is going to be true in all of these cases except this first one, right? And then and A and B, so this is false, but it becomes true with the not. This is false, this is false, this is true, but becomes false with the not. So truth table. So this is, we just look at the truth table for this guy here. This would be a 0, a 1, a 1, and a 1. So that's the truth table for the left-hand side. A or B for 0, 0 is a 0. Otherwise, it's a 1 for the rest of them. Right-hand side, 0 and 0 is a 0, not that is a 1. 0 and 1, not that is a 1. 1 and 0, not that is a 1. 1 and 1, not that is a 0. That's the right-hand side. And then we're ANDing those guys together. That. Does that look like our sum? So is this an example of an exclusive OR? Yep, I think it will. All right, so we can build an exclusive OR here using OR gates, AND gates, and an inverter. No harm, no foul. Carry is just an AND. So that part's easy, right? We have A and B. That's our carry. So here, let me just label this out here. So this is our sum. And our carry is A and B. Right? All right. Now we have two inputs and we have two outputs. How do we feed these two inputs into both of our outputs? Do we think of these like two different pieces of equipment? So this is kind of one machine, and this is another machine, right? So if I copy this guy, I put it here, I copy this guy, I put it here, those are two separate machines, and each one of those guys is going to have an output. The inputs to those guys, we have an A and a B as our inputs. And we're going to hook up the A and the B to that first guy, and the A and the B to the second guy. Is that something like what the guts of a half adder might look like? And inside there, so whatever is inside the box here is this stuff. We have our two inputs, we have our two outputs, and everything in the middle has our inputs mapped to two different little machines. Make sense? All right, so we could build a half adder out of and, or, and NOT gates in its entirety. Or we could just buy a half adder, which is made with and, or, and. Actually, realistically, it's probably made with XOR gates and a inverter and a NAND gate. It's probably how it's actually built, just because of the price of parts. But you get the point. Okay, so we've seen what the outputs are. So a half adder gives us a carry bit. We've seen the truth table there. And somewhere down here they should show us, oh yeah. So here's an example of sum. So this is essentially exclusive OR, and this is an AND. Here's our picture for this guy. 2 inputs, both inputs are mapped to both little machines. Here's the carry machine down here. Here's our sum machine up here. So that's what the inside of it looks like in terms of a diagram. So half adder works fine if we're trying to add 2 bits together, a situation that typically occurs only in the rightmost column of a multi-bit addition. So 2 bits, easy. The remaining columns have the potential of adding a 3rd bit, the carry, from a previous column. So what if we have 3 inputs now? So a half adder works for that far right column, where we know we don't have an incoming carry bit. Everything to the left of that has the potential of an incoming carry bit. Does that make sense? Has the potential for that. So a half adder is not gonna cut it. We need to look at something like a full adder that takes in 3 inputs: an A, a B, and a carry. Yeah, they're calling it a multi-bit adder, whatever. Oh, here, this is our full adder. Why'd they call it multi-bit here and then full adder here? Whatever. So we see this guy has 3 inputs and 2 outputs. Okay, so same guts on the inside, with the exception that we're taking in a carry bit as part of it. So if we look at here, inputs are A, B, and a carry, A, B, C. And we know our possible inputs for A and B are 0, 0, and I'm just going to throw the carry bit in there for right now. 0, 1, throw the carry bit in there. 1, 0, throw the carry bit in there. 1, 1, throw the carry bit in there. So these are possible inputs, and then our other possible inputs are 1s in all the carry bit positions. Make sense? All right, so those all the unique inputs to a full adder. Okay, and what should the outputs be? Well, again, we're going to have 2 outputs. So this is 0, 0. This is 1, 0. I guess I'll just keep going down here with it, and then I'll line it up. This is 1, 0. This is 0, 1. This is 1, 0. This is 0, 1. This is 0, 1. And this is 1, 1. So there's the outputs. Did I do all those right? 1, 0, 1, 1. Yep, I think that's right. Okay, so these are the outputs of our full adder. So just at a glance, half adder, full adder. Taking in 1 more input adds a lot more complexity to the circuit, right? So if we're creating a diagram, but we'll do this in a Boolean expression because it's more expressive for us, for a half adder, I'm sorry, a full adder, what would it look like? Got to take in 3 different inputs. Is the sum part still the same? Sum part, I mean, this piece of the equation is still the same thing we had before, correct? All right, so that's our exclusive OR. Okay, we'll steal our version of that. So that's this guy. I'll steal the whole thing just to give us a starting point. Okay, that's our starting point for the sum. And this is going to have an answer, correct? And what are we going to do with that answer? So I take the 0 and the 0, run it through this, and I'm going to get an answer. Then I need to take that answer, I need to sum it with this guy, right? What's that going to look like? If this is the answer of my left-hand side, what's my right-hand side? So I have to say A plus B plus C, and then produce a sum and produce a carry. So this handles the sum of only A and B. I need to take that output and I need to sum C into it. Well, how do we sum? Sum is take one number and add it to another number. So can I take this exact same thing, drop it down here, and replace all occurrences of A with this guy and all occurrences of B with C? Is that our sum? Where was that supposed to go? Where was that supposed to go? Is that over this one? Yeah, I need one more. Yep. Now there might be cleaner ways of writing it, but is this accurate? Should be, and that's just going to give us the sum bit. What about the carry? Carry bit is all these numbers. Do we see a pattern there? Well, how did we deal with the carry bit before? The carry bit was an AND. It was an AND of A and B. Zero and 0 is 0. 0 and 1 is 0. Go ahead.
If there are 2 or more 1s, so if 2 of our inputs are true, then we have a carry.
Okay.
So
we need to produce from 3 inputs this just the right column, truth table. 3 inputs producing 1 output needs to look like this. 0, 0, 0, 1, 0, 1, 1, 1. I will ask a question like this on the final. but it'll involve something else, not the adder, so you can't just memorize it.
I don't know if there's a shorter way to do it, but you could just
Doesn't matter. Doesn't matter if there's a short way. Accurate way first.
right. So you could do A and B, or A and C, or B and C. And then parentheses around all
The chunks.
yeah.
If you leave it on parentheses, is it still correct?
In this case, order of well, not necessarily, because in Boolean logic, order of operation is not guaranteed.
Okay.
So it would really just depend on how the person interpreted it. So I would say the parentheses are always going to be preferred because it clarifies. So A and B, or A and C, or B and C, that gets us our 0. A and B, that gets us our, that's a 0. So anytime we just have one, it's guaranteed to be a 0, right? Is that right? Yes. Anytime we have 1, it's guaranteed to be a 0. Anytime we have 2 1s, we're guaranteed to get a 1 out of one of these 3 chunks. So whether it's the A and B that are the ones, or the A and C that are the ones, or the B and C that are the ones, one of these will produce a 1, and in the OR, we'll get a 1. So here's an example where we have 2 1s, we get a 1, 2 1s, we get a 1, 2 1s, we get a 1, 3 1s, we get a 1. So anytime we have 2 or more 1s, we get a 1. Under all other circumstances, we get a 0. So this will do it for our carry, right? So that's the sum. That's the carry. Draw these up, hook all of our inputs up to all of it, and feed everything through. Make sense? So this would be the stuff that's on the inside of our full adder. A lot more complex, isn't it? And there's probably ways to simplify this and make it a little bit cleaner, but it's hardware. We leave that for the job of the, once you have the correct answer, simplifying it to the parts that you have on hand. So you got to kind of solve the problem based on what you're buying in bulk. That's why we have our universal gates, the XOR gate and the NAND gate. So all of our other gates can be implemented in terms of those 2 gates. And some creativity is the punchline. Okay, so full adder in a diagram looks a lot like a half adder in a diagram, but we see that the insides of it are substantially more complex. And when we're actually doing math, we can get away with a half adder on the rightmost bit, but everything else needs to be full adders, right? So does that mean if we're doing, if we have 16-bit registers that we need to be able to add out of, in order to do that math, we need to have 15 full adders and one half adder? Well, why not? Here, we'll just do a simpler example. Let's say I want to take, we'll do 8 bits. There's an 8-bit number. And another 8-bit number. And I want to add these together. Aren't I going to need a half adder for these bits? A full adder here, 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 and a full adder here?
Couldn't you just use the same full adder and just plug in the different? Just reuse the same one.
Okay. So let's draw some pictures of our adders. That's our half adder. So half adder Oh, this will actually work. It's actually weird. Why does it put a space if I do 3 in a row, but not if I do 2 in a row? All right, so that's our half adder. 2 inputs, 2 outputs. Full adder. Three inputs, 2 outputs. So if I have these 2 pieces of equipment laying around and I want to add this 8-bit number, how would I do that? I need to wire this up. This is where things start getting fun.
You and I have different ideas.
Well, the easy part is what? The easy part's the use of the half adder, right? We only need that guy once. So what are we going to do? We're going to figure out how we can organize this. Let me do it this way, if you will bear with me for a second. That's our first number. Oh. And this is our second number. And these are the far right bits. All right, so this is A and B. So we're going to take these 2 bits right here, 0 and 1. Do I have the ability to? Oh, that's going to suck. Okay. That's not what I want either. So we'll take this guy, hook it up there. Take this guy, and hook it up there. And out of that, I'm going to get a sum. So we'll say this top one is a sum, and the second one's the carry. This is S. And this is C. Sum and carry. So we have those 2 guys. The sum that's going to come out of there is going to be one of our outputs. It's going to be the far right bit of our output, correct? But the carry needs to go where? This carry feeds in here, right? So we'll feed it in directly first. So we hooked up our carry bit. Now we know that the half adder bit is going to go to our final result. So we know our final result is going to be 8 bits, right? So this is our final answer. So we can go ahead and take this guy and hook it up. So we've wired it to that output. Carry went in for one of our inputs here. Now we're going to have our next inputs come in for A and B. So here's A. Take it there. Here's B. There. All right, so now we have A plus B plus C, which produces an output. The output's going to be what? The sum and the carry. S and the C. What do we do with our sum? Sum goes to our buckets, always. Whatever comes out of here is going to be our next sum coming out of here, right? So what we're going to do here, just going to create some awesomeness. Now imagine, in the early days of dealing with this, you would have had to have all these wires soldered together or twisted or whatever to make this work. All right, so our sum is always going to go to these buckets. And we're not even considering how do we determine which bucket it goes to, but that's actually okay in this example because this is going to be a nightmare enough. And remember, this is just for an 8-bit number. All right. So we have all of our sums hooked up. What do we do with the carry? The output of this guy goes back in where? Feeds right in for the next input. I think I might get to use this guy now. You got this. Shake. Good enough. Close enough. Goes right back into our input. All these other guys plug in to our inputs. So we have these same two lines drawn over and over and over and over again.
Thought you were not going to do that.
Would this actually end up working? Logically, it makes sense. But how do we make sure that these guys feed in first with the output of this before the next guys feed in? It's got to be an order of operation here, right? So think about the mechanics of this. So we're going to have 16 people lined up. Just kind of do this as a human problem. So we have 16 people lined up, 8 people on each line. Okay, the first 2 people are lucky. We're going to run them over to the half adder, toss them in. It's kind of got a burning smell, the half adder. So they'll probably be okay. The other ones you hear grinding. Okay, so you take them over to the half adder, now they're done. That was the easy problem. Look how simple our half adder hookup is. No harm, no foul. We've even made the full adder look less scary because we didn't draw on all the lines over here. All right, so now we've dealt with the first 2 people in line. We have 7 people in each line left. We need to make sure that we take the next 2 people, feed them through our machine here before we take the next 2 people, before we take the next 2 people, before we take the next 2 people, so on and so forth.
Hopefully they don't get rid of the first two.
There's like cattle going to slaughter. How would you pull that off? Human beings were really good problem solvers, right? We would just figure it out. It's like, oh, well, you're going to go first, and you're going to go second, and you're going to go third, and so on and so forth. But if we're really wiring this, and we're trying to have all these things happen in a certain order, they have to fire in a certain order, we have to essentially have the door closed on these guys before the next ones can go in. We're also doing something multiple times. Sounds like a loop, right? How do loops happen in hardware? We've talked about it in here. Long time ago. Kind of connecting early parts of the semester to later parts of the semester. Remember pulses? Can't we have a frequency that this is operating at? How are processors measured? Hertz. Gigahertz, megahertz. Oh, what's a hertz? It's a measurement of frequency, correct? It's a timing thing. So digital logic works very much on timers. And we're going to sample at some sort of rate. Make sense? And that's what's going to create our loop. Or at least that's what may create our loop in this example. You know, there's actually some more modern way of handling some of these things for increased efficiency, but to get an idea on how this hardware stuff kind of works. You know, we need to take it from the idea of writing software where we have loops and things like that and conditionals, and now we're feeding things through hardware. And we have kind of 2 different things we can do. We can build this circuit using a whole bunch of adders. That would be the easy way, right? If we know we need to add 2 8-bit numbers together, can't we get 7 full adders? 1 half adder, and just hardwire all the inputs up and be done with it? Yeah, and that's when we start getting our gymnasium-sized computers. That's for adding 2 8-bit numbers together. God forbid you want to do a 16-bit number, or 32, or 64. Start running into real problems. So we see how this can be hooked up and how we can map the carry back onto itself. And we can map various inputs onto itself here. And the half adder just keeps doing its job over and over and over and over again. Same thing over here. We're going to have some sort of pulse thing. Could be some sort of wouldn't be a multiplexer. No, let's just say some instrument that would sit here, and each pulse we would shift it over to the next output bucket. Make sense? Okay, so we can certainly build this with a bunch of LED lights and stuff like that and have it light up with the ones and zeros as to whether or not it's, for what the answer is to do the math. But there's a lot of wiring that goes into that. Now that's the advantage of having these things like half adders and full adders, as opposed to having, what if instead of each of these we had to feed everything into those AND gates? Basically it's doing the same thing, but it's going to look a lot more complex, right? So this is our hardware version of what? It's a method, right? This is a method. 3 parameters, 2 outputs. And we've encapsulated the details inside of it. You can think of it in terms of objects too, that's fair. But this is a method that does something. So its representation is object-oriented. Its function is like a method. So because we have this, now it's a reusable, quote, chunk of code that allows us to do something over and over and over again. That kind of makes sense? Okay, here's our circuit for our full adder. So see how that guy looks a lot nastier than this guy. So half adders and full adders sound closer than they actually are in implementation. And in general, think about how trivial a full adder is in the world of how complex computers are. Isn't it amazing our computers keep getting so small? The amount of stuff that's in there. A full adder is like blip on the radar. Probably doesn't even show up as a star in the night sky. It's not emitting enough light. All right. So, another tool, built-in tool that you might get is a 7-segment display. You've seen these, like on alarm clocks maybe? Probably a bunch of other places, but some of us, I'm sure now, have alarm clocks with a 7-segment display on it. Or in your car, clock in your car. Okay? So, and see, look, most everyone has seen one of these. We have. So this is what these guys look like. So these are a bunch of variables. All right, so each number that you want to have on your 7-digit display. Okay, so this is our 7-segment display, which has the capability of showing all 10 digits, 0 through 9. Okay, so each of those digits is going to have its own mapping for what the inputs are going to be. So think of this as being a machine that has 7 inputs. Okay, or rather, 7 outputs to the screen. So depending on whether these are on or off, different of one of these 7 segments, or some of these 7 segments will be on, other ones will be off. So here's our 7 outputs, which are going to be wired in, hardwired. So A is going to be hardwired into this segment, B will be hardwired into this segment, C is into this segment, so on and so forth. So if you apply power to all of them, you would get an 8, right? Okay, so this is all just electricity. So here's our 7 outputs. And the nibble coming into it, A, B, C, D. Why is it a nibble?
4 lines per number.
8. And 8 is 7 lines, isn't it?
Oh, yeah, but
So why is the input a nibble? Somebody who hasn't answered yet today. It's an easy answer related to the last question of the previous homework assignment. was asking you what kind of numbers you should use to represent like a phone number, and I don't remember what the other ones were, but that question. Why is the input here a nibble? What am I trying to represent in my outputs? Digits, right? So I want to be able to show a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, 8, and a 9. So why is the input a nibble?
All the possible inputs that can be put into it can fit into a nibble.
Okay, what do you mean by that?
Like, with a nibble, you can go to 9 without requiring more bits.
Okay, so why can't we just do it in 3 bits? Why do we need 4? Can't count to 9 with 3 bits, right? No, I just wanted to make sure he had it. There's been some question. Okay, we need 4 bits, a nibble, in order to fully represent all the numbers between 0 and 9. A 9 is, you have the 1's place, the 2's place, the 4's place, the 8's place. So a 9 requires 4 bits. 1, 0, 0, 1, right? If we only need to deal with 0 to 8, we can do it with 3 bits. But 9 requires that 4th bit. So our input is the nibble representation, the binary representation of the decimal numbers 0 through 9. Output is which wire should light up on your 7-segment display. That make sense? You guys are going to hate me. It's going to be so good. It's such a good assignment. All right. I'll just do it in. All right, here, we're going to make our own class here. Create a new class. 7-segment. Okay, and 7-segment is going to have a private int A, private int B, private int C, okay, so there's our 7 segments. And I'm just going to kind of get us started on this. That way you have to do a bulk of it for your assignment. So good. You know, actually, I'm just going to take an integer array. It'll be easier. It's called inputs. Realistically, I should have probably done these as an integer array as well. Nah, screw it. Leave it. This probably is more true to life for the 7-segment anyways. These are each individual wires. So makes sense. We'll just make it convenient for us to pass the stuff in. So we'll say this dot A is equal to inputs at bucket 0. I think I did one too many, right? I lost count, but yep, one too many. All right, so when we create our 7 segment, we'll pass it in an array, which will allow us to initialize zeros and ones for all of our segments. Then we're going to have a display. And the display method is going to display this particular 7 segment output. Okay, so again, looking at this, 7 segment looks like this. Now, what I might do is I might represent this as a grid. Okay, a 2-dimensional array of chars, probably, where this is a bunch of hyphens, this is a bunch of the pipes, straight lines, hyphens, pipes, straight lines. Okay, so as an example, as a starting point, I'm going to say char array output is equal to a new let's just start with 10 by 10 might look stupid, but that's fine. And then what I'll do is across the top, the bottom, and the middle, I'll go ahead and just do hyphens all the way across, full row. So I'll just hard code it in there for now. For int I is equal to 0, I is less than, I'll just hard code it in the 10 for right now, I plus plus. We're going to need this for 3 different rows. Row 0, row, so we have 0 to 9. So 4, or maybe row 5 and 9. Not going to look real even, but whatever. It'll be fine, close enough. So we're going to say output at bucket 0, bucket I is equal to a hyphen. Output at bucket, what did I say, 5? 5i is a hyphen. And output at bucket 9i is a hyphen. All right. Similarly, we want to do the down direction. So we're going to say the left, this is going to give us an 8 to start with, so I'll give you a starting point. The left is going to be pipes. So that is row I, column 0, and then row I, column 9. So output at row I, column 0 is equal to a pipe. Output at row I, column 9 is equal to a pipe. Oh, thank you. All right, so that'll fill it all up. And then I'll quickly display it. For int I is equal to 0, I is less than, I'll just hard code it, I plus plus. For int j is equal to 0, j is less than 10, j plus plus. System.out.print. Output at bucket I, j. And then system.out.print. Lin, empty string, kick it down the line. Okay, so right now our inputs here are relatively meaningless. Okay, they don't mean anything because we're just displaying something with it all filled out. And just to prove that real quick, in our last minute, here's main. Now we're going to create an instance of our 7 segment. And we actually do need to give it 7 numbers, otherwise it will crash because I'll try to access buckets that don't exist. So that'll be all of them on, which should produce our 8. Is it seriously not going to let me do that? Okay.
Not letting you do that.
Not directly. So I'll pass an input, and then we'll say ss.display. I filled it in there.
Spaces in between.
Oh, I didn't. In the empty things, we don't have spaces. That's fine. So, yeah. Yeah, so we need to fill it up with spaces first. 2 seconds. Only gonna take 2 seconds. Just gonna copy this, just so you have a good starting point. There's this. Output at ij is equal to a space. So I'll pre-fill it with spaces, then fill up the other parts. And there's our 8. The output looks a little funny just because of this thing. So your job for your homework assignment is, given this as a starting point, allow this guy to take in arrays of different inputs and display the appropriate number. Okay? You do not have to do the mapping from a decimal number to a to the 7-digit number. We'll do that in class next time. So that means you should be able to pass in 1111111. Let's assume that was 7, and it'll turn all of them on. 1111011110. Assume that was 7. It'll turn the correct ones on. Make sense? So be able to take inputs and light up the correct lines, rather than what we're doing down here in our display right now, just hard coding it all being on. So right now the output is equivalent to what all ones should be. That makes sense? All right, I will see everybody on Thursday.